Hello, this is a quick video guide to using XFLR5. It'll explain how to use the software and how to create an aircraft within it and how to get useful information out of it. So this is information such as aerodynamic data, structural loads through particularly the wing, aerodynamic stability information, is the aircraft stable in normal flight, and you can also get a lot of various other important information out, such as drag factors, lift and drag at certain flight conditions, static stability, static margin I should say, and other interesting information that you'll need when designing your own aircraft, especially for your competitions. And this isn't really stuff that you can do by hand, so that's why we're showing you how to do this in the software. For those of you in particular, if you're an aerospace student, XFLR5 or XFLR5 uses a combination of thin airfoil, lifting line and vortex lattice approximations to model the aerodynamic effects of aircraft wings and fuselages. This is a much more simplified model than the full Navier-Stokes solver, which is a nightmare, but it's pretty accurate, especially for the range that we're going to be talking about. There are problems with this simulation when you start to go above, say, Reynolds of 1 million. That applies to jet aircraft, full-scale aircraft, and so on. And there are problems with going higher than Mach 0.3, although there is a correction that you can do to make it go to Mach 0.8. What this means is that it's perfect for our modelling, which is UAVs. So these aren't, well, if you're doing a UAV that's going more than Mach 0.3, you're probably not going to be watching this video, hopefully. I'd hope that you're a little bit further along. And I don't think you won't be designing anything that will be going over 1 million Reynolds. I shouldn't really think so anyway. And so yeah, long story short, this software is great for the type of aircraft that you're going to be building with us. More information about limitations and a bit about how this software works and more details in general can be found in the associated XFlyer for Dummies handbook that will be provided. Okay, so first of all we want to actually download XFlyer, so just go to your browser, XFLR5, go onto XFlyer, downloads, click download latest version, and there you go. Once that's done, follow the usual installation process, so extracting all the files and such. I'm not going to do that now because I've already got a version of it that's downloaded. When you click it and you load it, it should look like this, just a big sort of like empty black screen. But it is working if it's like this. Okay, once you've got that together, you're going to come up here to File and you're going to look at these 4 tabs. These are the design stages that you'll go through during XFlyer, and you'll go through them in descending order. So you'll start up here on Direct Foil Design. This is where you go to put all of your airfoils in, so the airfoils that you want to use on your wing, on your tail, and so on and so forth. If you're a 3rd or 4th year aerospace student and you know a little bit more about airfoils, or you're just that eager, you can come to Xfoil Inverse Design. This is where you'll go to sort of reverse back. So you'll define what kind of needs you want from your airfoil, and you can get the airfoil out as like a custom design. But you're not going to be worrying about that for this tutorial. Next is Xfoil Direct Analysis. So once you've got your airfoil, you then need to do a bunch of analysis on top of it. So for a certain angle of attack, for a certain Reynolds number, what kind of, say, lift will you get out of it? This is the type of analysis that you do here. It'll then collate all of that analysis and put that into sort of like into a storage for you, so that when you come to the final stage, your wing and plane design, this is where you'll use that data to actually simulate, okay, how does it perform for this type of body? It'll take that data and integrate over the wing for those airfoils. And then that's how you get overall drag factors out and overall coefficient of lift. But as I said, we start here on Direct Foil Design. This top section is a plotter for your airfoils, so when you input them, they'll show here. This bottom tab is the list of airfoils that also shows some information, including like thickness and camber. You can click here to show the airfoils when they're in. There's two airfoils that we're going to be using in this analysis. Of course, there's like millions of them, or arbitrarily as many as you want. For this one, we can put in an airfoil by coming up to this tab up here, foil, and coming down to NACA foils. NACA foils are foils that can be generated based off a number. Each number represents something different about the foil, and it can generate it based off of it. So if your airfoil is a NACA airfoil, it's easy. You can just put it in here. So that's 0009 for 100 panels. Okay, and that's your NACA foil. But we also want to use a foil that isn't included in the NACA series, and therefore isn't necessarily generated by XFLR easily. To do that, we can just come to our browser, and we're going to type in airfoiltools.com, navigate to the website, and we're going to type in the airfoil number that we want, S4062. There we go. FYI, this is a website that includes millions of airfoils from all kinds of like random different research studies. They include like all types of data collected from them, like drag polars and so on and so forth. So if you wanted to actually search for a custom airfoil, you can do that here, no matter, like, there's no problem with that. Just going to click search for this airfoil. It's this top one here. So this is the airfoil we want, and as you can see, some drag polars and information on the bottom. We come to Selig format dat file, click that. Takes us to this page with coordinate information that describes the actual curve of the airfoil. We're going to right click, save as. We're going to call this, you should call it the actual name just so that it stops confusion, but I'm going to call it foil.dat. The .dat at the end is really important, make sure you put that, even though it's a text file. I've already saved one, obviously. Okay, I'm going to close this down. Up here, back on XFLR, we're going to go to Open. Go on the foil. That include it, yep. So if I just hide the other foil, you can see the airfoil is now included, the full shape. And that's the original foil. So once you're happy that you've got all of the foils that you want and they've loaded in properly, come up to File, and we've just done the direct foil design. We don't need to do the inverse design, so we come straight to direct analysis. We click on analysis, and we can either do a batch analysis or a multi-threaded analysis. They both do the same, it just depends on how good your computer is. So as you can see, this one, it looks exactly the same here with all these different inputs. This one's got a little graph. If we go to a multi-threaded one, it's exactly the same except it doesn't have a graph, just because obviously you'd be doing multiple threads. For this one, obviously I'm doing all of 12 of my threads. You can, up here it has either current foil only or foil list. We're going to select foil list because we've got multiple foils that we want to do, so we're doing both here. The first batch variables here are the Reynolds range that you're going to be doing. For those of you who haven't covered Reynolds yet, it's essentially the ratio of the inertial forces of a fluid against its viscous forces. The lower the number, the more viscous the fluid. The higher the number, the more the fluid is dominated by inertial forces. Our aircraft will fly in regimes of about somewhere in the hundreds of thousands of Reynolds, sort of between 100 and 600,000 Reynolds. Turbulent transition occurs at about 400,000 Reynolds, so we want to make sure that we cover that range as well. Because there are stall cases and edge cases, we'll be making sure that the range is between 20 and 700,000 Reynolds, which, in fact, actually I'm going to make that 800,000. I'm going to do this in increments of 5,000. Essentially, you can change these values. You can change the values in the increments to be larger increments, so that the analysis takes less time. As I said, I'm on a good computer, so I can afford to sort of brute force it a little bit. But if it's taking a bit too long, you can make it. You can turn the increments to be larger. We're not going to change the Mach number because we're at a very low speed. This is where you would go if you're going to be doing Mach greater than 0.3, and your fluid is no longer incompressible. Don't touch the encrypt for now. It's to do with the free stream turbulent kinetic energy. We'll leave these numbers as well. The final one is the analysis range for the angle of attack. So we want a positive and negative angle of attack, and I'm going to choose to do them between -10 and 15 degrees in increments of 0.1 degree. So I'm going to hit Analyze. Just to show as well, this is my task manager, and you can see that, yeah, it's throttling the CPU a little bit, but that's okay. Okay, analysis completed. Didn't take too long. As I said before, more details about what each of these numbers mean can be found in the textbook. Not textbook, sorry, the actual PDF that we'll give you. Okay, so I'm going to hit close. There's all of our data projected. You'll find how to interpret this data as well in that PDF. So we're done with interpreting the data now, and we can go pretty much straight to the aircraft design. So File, Wing and Plane Design, and click the little plane tab if you're not already on that. These are for graphing after we're done with our analysis, but we're not at that point yet. Okay, so to start a plane analysis, we come up to Plane, define a new plane, and here I'm going to call this Tutorial 1. When we do these analyses, it's up to you whether or not you include the body. Today we're not going to be doing the body just because we're going to assume that it's a carbon rod. If it is a carbon rod, then it's probably too small to really consider. However, if you're doing a body that might actually impact on the aerodynamics, so this is quite a large body or one that takes up a lot of the sort of where the wing would be, then it might be worth your time to actually include the body. But here we've got a main wing to go over, elevator and a fin. So this is the wing editor. Here is our graphical output of what we'll have. This is a bunch of information that we'll get at the end based off of our wing as we change the information that we'll put in here. It's a coordinate space. If you can't quite see on my video quality might not be great, but you can see the Y, X and Z axes. And that corresponds to these values here. So if you scroll in and out on the graphical image, you can zoom in and out, and if you left click you can grab and move, and if you middle click on your scroll wheel you can move the wing around, and that'll be the same for the other 3D model when you get to that later. It's a symmetrical wing, so you do one wing section and then it's repeated on the other side. So if I change this is your outer section, this is your outer airfoil. So if I change this to say 1.5, we've made it an extra 0.5 meters greater on this side. So your total wingspan is actually 3 meters because it would have been 1 meter each way. So that's 2 meters plus an extra 0.5, which comes to 3 meters. And again, obviously, if you change it to 0.5, it halves from the original, which is 1 meter. Next is your chord. So if I zoom in here a little bit, your wing will have a center sort of thickness. So it's this dimension here, and then you've got one also on your outer edge. That is your chord. It's how long your airfoil is going to be. And of course, obviously, If we change this foil there, it's like 10, becomes massive. Way too big. But if we also make it, say, 0.01, becomes tiny. So that's what you change here. So I'm going to change this to just 0.1 for now. Offset is how far back from the leading edge it is. So if you take this axis coming out here, it's 0.1 backwards. Sorry, this is 0.07. If I make it 0.1, it'll actually move back a little bit more. If I make it something absurd, like 1, it becomes way further. This is how you get this is how you input sweep into your wing, but it's measured in terms of offset rather than sort of degrees. So let's just give this something sensible. You don't have dihedral on your final wing piece, but you can do it on your center. So if I rotate this around here, you have these ones to click through as well if you're struggling with your middle click like this. So let's get a top-down view. Oh, sorry, no, front view. Sure. If I put a dihedral in here, like 10 degrees, you can see that the wing sort of, it's got 10 degrees banking up on each side. We'll talk about this in our aircraft design lecture, but this is one way that you can improve stability, for example, to a certain extent, depending on your aircraft design. For this model, I'm going to put 0 degrees dihedral for now. If I show you the wingtip again, twist is how much, so right now, the chord is completely flat in the plane, but if I change the twist to be, say, -30, it'll actually pitch down now. If I make that, say, -80, which is absurd, it's pitched down quite a lot. Put that as 0 for now. If you're doing specifically for like flying wings, you'll have a little bit of negative twist. This makes the wing a little bit more stable. Next, we have the airfoil that we're going to be putting in. So if you just by clicking them, you see that the flat plane that we've just been seeing for the wing becomes a 3D object. That's not the airfoil that we want to be using for the wing, though. We've picked this airfoil, so we can update it. And there we go, there it's updated. And you can see the nice curve through the bottom now, like that. You can do transitions between airfoils, and XFLR will just, if I click out of that, it will interpolate between these airfoils as it goes. So you can see that this one's got a bit of a bow in on the bottom, whereas this one bows out. But we're just going to do simple wing for now. Zooming back up. Over here, there's some things to click about, like what you want to see on your GUI. So you can remove your axes, you can take the surfaces off, you can put the foil names on, but what we want to see is the panels and then without the surface for now. This is basically the level of analysis that the software will actually do. We can increase or decrease the number of panels. So if I put, say, 2, there's fewer panels, say, going across the x-axis now. But if I change this to, say, 30, there's 30 panels now. Keep that as 13. Change this to cosine. We want it makes more sense if we keep all of these as cosine, and then as well we'll keep this as 19. Will be fine. And that's how many panels you want. You can increase the number of panels for a higher fidelity model, but at a certain point you're just making it more complex for basically no extra result. Put the surfaces back on. We can also put, insert sections. So we're going to insert a section after section 2. Another sort of a wingtip section. And really, you can sort of play around with this and do what you want. So on this one, I'm actually going to want some dihedral, a little bit. Sort of 10 degrees. Let's see. Just make this a little bit random for a bit. Something like that. Honestly, you can do sort of whatever you want with this. It doesn't really matter for now. this is just to show you how it all works. So we're going to hit save. And now we need to do the elevator and the fin. These work in exactly the same fashion. So you come to define, and you've got all the same tools that you just saw before. So for this one, I'm going to put NACA009, and I'm actually just going to leave it as is for now. Same goes with the fin. Okay. When these are outlaid, so if I just actually hit save now and show you, this is the plane put together, and you can click around as well and have a look around. If you want to say make the tail plane move further back, you can either right click, go to current plane and edit, which takes you back here, or of course come to plane and current plane, edit, and you come to here. These features of the plane are located in sort of a coordinate space, and whenever the analysis is done, it will make sure that, for example, so this elevator is 0.6 meters back from the from right now, because the wing is at 0, 0, 0, it would be 0.6 meters back from the leading edge of the wing. We can change this to be 0.8, save, and watch it move a bit further back. Going to keep that as is for now. I've just noticed as well, you'll probably have this little tab as well. It was just on my other screen. I hadn't even noticed. I'm just going to put it over there for now. Before we can actually get on with any analysis though, we need to include a mass model. So we come to current plane, edit, plane inertia. You can either do the inertia of the plane based on sections. So you could do like, here's the mass of the elevator section, for example. And the same for the wing and the fin, or you can just do point masses here. If I make this a little bit bigger, these point masses. So in a final all-up model for a BMFA competition, for example, you'll need to do a little bit of all of it. But for this one, we're just going to do point masses. So for example, I'll type in here. This one's going to be for the motor. It's a good idea to name these as you go, because otherwise you'll get confused. I've learned that from past mistakes. Going to do a battery, and we're going to have a payload. These are just sort of random values, but I'm going to say that the motor weighs 0.2 of a kilo. The battery weighs 0.3 of a kilo, and it's going to carry altogether 5 kilos, for example. And that brings our total mass here to 1 kilo. If we did that now, all of these would be on the same spot, which is at 0, 0, 0, which is the leading edge of our wing, right in the center. So I'm actually going to move them to try and be kind of realistic to what it'll actually be like. So the motor will be a little bit ahead, which will be like minus 0.2 meters or something, just ahead of the leading edge. The battery will be, say, 0.05. These are just random numbers. I have no idea if the plane's even going to be stable. 0.15 for the payload. I'll hit save. Save again. On this little tab, I should have shown before, but you've got all the same display features that we've seen on the other stages. So we can take off the axes, and we can take off the outline or whatever. But more crucially, just because we've done the masses, we can hit masses, and we can see the motor's comically far ahead. Well, actually, no, that's okay. It's whatever. I don't really care anyway. It doesn't really matter for this analysis. It's just a completely made up plane. But yeah, so now you've done your mass model. So now we're ready to do an aerodynamic analysis of the plane. We'll come up here to analysis, define an analysis, and we're going to do a type 2 fixed lift one. This is essentially for any angle of attack, it's going to make sure that it's flying in a sort of a cruise state. So it's not necessarily got more lift than weight or more weight than lift. Going to hit save. In this plane analysis tab, which is now a little bit more active, you can hit sequence, and we're going to do it We're going to do it for a range of, yeah, minus 5 degrees to 10 degrees in increments of 0.5 degrees. And we're going to hit Analyze. For today's session, it's not a big deal that we've got some errors, although when you do your final model, you're going to want to go back and make sure that you don't have these errors. All this means is that for certain angles of attack, so for example, there are a load of errors here for 10 degrees, it means that when we actually have a look at this tab here, we can't actually see 10 degrees. So the ones that are actually working there, so for example, 5, 4.54 and so on, the analysis for them was successful. You'll see that there's two types of error: is outside the flight envelope and could not be interpolated. The is outside the flight envelope error essentially means that you haven't done the analysis to a high enough or low enough Reynolds range. These are usually sort of edge cases. For example, the airfoil might have stalled, or some other weird effects are causing the Reynolds to be sort of weird for that particular section, like interference between like changing airfoil shapes, which actually, yeah, it's the outer board sections that have gone wrong. So that's when it became super small. But so that can be fixed by just going back, and you can go back to do the direct analysis, and you can run more analysis on those particular sections so that you've got more data, so that when you retry this, like you don't have to restart the file. When you redo the analysis, you can run this without having these errors, and you can get your 10 degrees. So is outside the flight envelope is when you haven't done it to enough Reynolds, either high or low, or the fidelity. And the could not be interpolated, it means that it wasn't set to a high enough or low enough angle of attack in one of the earlier stages, the one where we did it to, I think we did it to plus and minus 10 degrees. You might want to be a little bit more adventurous and actually go to like plus 15, minus 15, or plus 20 or minus 20. Depending on your PC, for all of those situations, for example, the Reynolds analysis that we did earlier, you would probably want to do that for a larger range, more rigorous. That's fine if you're on a good PC. If you're not, you have to be a little bit more sparing with how much you've got. Okay, so I'm going to close this now. Okay, so now that you've done the analysis, you can start looking at some of your results. I'm going to take off the masses here, and these are your results. You can sort of toggle them to actually see what's going on. I wouldn't recommend toggling them all, because there's an awful lot going on. So for example, the streamlines, so as you change your angle of attack, you can see them develop. So it's probably easy to see on the tailplane. Becomes more chaotic at a low angle of attack. Or not low angle of attack, high negative angle of attack. And at a high angle of attack as well. Becomes like the wash is reversed. You can also see surface velocities. And so already we can start to get some information out from our analysis. Since all of these are in a flying sort of steady state, you can see that for 0 degrees of attack, it's 11.78 meters per second is your cruise speed. If I increase the angle of attack, you can see that your speed goes down. So you're flying slower because you're getting more lift at a higher angle of attack. If you decrease into negative, you actually need to be flying at a higher speed. Very fast actually, in order to fly at a constant altitude. Well, with constant lift anyway. There's other information you can get out as well. These are things that we'll talk about in our aircraft design lectures. Things like wing loading, which you can actually see better if you come up here to this one that's like a semicircle. It should say odd points, I think. Yeah, odd point view. this is your bending moment. When you come to do your structural analysis, particularly the structural analysis of your wing, you're going to need this information later on so that you can see what your root bending moment is like. And of course you can change that and see what it's like at different angles of attack. The PDF will show you how to, so for example, you can go to current graph, export, and you can export this as a CSV file, which you can then take into like Excel, for example, and do more detailed analysis with that. So that's some of the analysis that you can get out now. More analysis based on this, for example, so you can come up here now instead to, these should be drag polars, yeah, your polar view, and you can investigate these graphs to determine certain features about your aircraft that will be described much better in the PDF. So for example, this would be your CLCD versus your V graph. To change this, you just right click, define graph settings, and then there you go. You can change this to be whatever you want. This one would tell you where your most efficient speed is. It seems like this is actually quite a slow flying plane, and actually the graph hasn't fully developed here yet. It's lower than we would actually expect. You would need to have this for if you wanted to see the proper shape, you would need to do this analysis for higher angles of attack. But the PDF will tell you all about what each of these graphs mean and how to interpret them and what it is that you're supposed to be looking for. Okay, and so lastly, we're going to do a quick stability analysis. To do this, we're going to come up to the top right here, analysis, define stability analysis, and we come to this page here. This should be the standard sort of configuration here, but we're going to want to come to control parameters, and we're going to go to elevator tilt, and we're going to change this to 1. And then we're going to hit save. Okay, and yeah, these are the values that you're going to want on your analysis as well. So again, sequence between -10 degrees and 5 degrees in increments of 0.1, and we're going to hit analyze. Store out point data as well, obviously. Once again, we're expecting to probably have some failures or some errors. This is just an off-the-cuff analysis. If you do run into them, you'll go back and do a more detailed, rigorous analysis of, in particular, your airfoils. Yeah, errors encountered. Hit close. Let's turn all these off for now. Here we get to see some actually interesting animations. So you can, this is toggling the speed of the animation, and this is your amplitude that you want to go for with it. So I'll keep that there. If I hit animate, and you'll see how in a particular mode, the modes will be described in more detail in the PDF. These are different like sort of modes for stability. So if there's a perturbation in roll, there's a perturbation in pitch, perturbation due to extreme wind, due to like a side wind speed. The PDF will show them all, but if I hit speed, and you can see that that's stable design. When there's this particular perturbation, it returns to normal. Mode 2 as well. Mode 3. So this is a phugoid mode. And then there's also the lateral modes. Oh boy. Well, I mean, I guess that's kind of stable. If we take this to a lower speed, so